Okay, so we're continuing on with our lecture for Chem 113 for proton NMR spectroscopy. So in this case, we are given the following NMR spectra, and we're asked to draw a structure matching the following proton NMR spectra. So we're going to be doing some examples to practice and develop our skills. So I'd like us to work through this example over the next 5 to 7 minutes. And don't be shy to share your responses and thoughts as we work through this NMR spectra in the chat, verbally, or using the annotate tool. So we're looking at this NMR spectra and we're given the formula. So to give us a hint, if we calculate the DU, we have 2 times 4 plus 2 minus 6 over 2. That gives us a DU value of 2. Okay, so that tells us we can have 2 double bonds and or rings. So I'd like us to take a look at this spectra. Let's try to assign the functional groups associated or adjacent to each of these proton signals. And I'd like us to use the integration values to begin to estimate the number of protons found in each signal. So we have the integration values shown below. And looking at the integration values, what do we think? What is the simplest ratio of protons? One to one to one. Yep, that's a great first look. Now, how many protons do we have?
6.
6. So 1 plus 1 plus 1 is 3, right? So 3 times what would give us 6? So rather than 1 to 1 to 1, it should be 2 to 2 to 2. Does everyone get how we used the overall proton count to note the actual integrated value for each of our peaks? 1 to 1 to 1 adds up to 3 protons. We obviously have 6, so we need twice the integration for each of our signals. So this gives us a 2 to 2 to 2 ratio. You can also tell that by the fact that you have triplet patterns, which are indicative of 2 proton groupings. Okay, so the next step, and one way that we can start facilitating this discussion, is noting the chemical shift, integration, and multiplicity of each of our peaks. So let's just fill in this table now. So what do we fill in for this peak? What would we fill in for this peak? What's the chemical shift?
About 4.3.
4.3, yep. What's the integration?
2.
What's the multiplicity? What does it look like? Singlet, triplet.
Triplet.
Triplet, yep. Okay. And
which would mean N is equal to 2.
Yep, we have 2 hydrogens adjacent. Yep, exactly right. Another piece of evidence for this 2-2-2 integration pattern. Okay, what matches 4.3? What matches 4.3? What kind of proton does that resemble? You may need to open up your table earlier on in the note set. What does a chemical shift of 4.3 correspond to?
Would it be the ether or ester?
Ether or ester, yep, we're not sure. But since it's farther downfield than usual, this ester assignment seems reasonable. Yeah. So this is a methylene group, a 2 hydrogen group attached to the oxygen attached to an ester. Okay. So let's keep going. Let's keep going. What about this next signal? What about this next signal?
It kind of looks a like a splitting, but I don't know.
Oh,
Like that's a doublet of triplets or something.
But what's,
Or are they two separate peaks?
there are two separate peaks.
Okay, so it's a triplet.
Yes, so this one is a triplet. And to answer that question, why are there two separate peaks? So one trick that you can see is that when you have a splitting pattern, you'll often see this sort of convex pattern where the center peak is the highest of your splitting pattern. The other thing you can do is if you note the distances, in the splitting pattern and the separation between the peaks, that allows you to calculate the J values. You don't need the coupling constant values in this case, but nonetheless, you can tell by the separation of peaks whether or not a set of peaks are part of a multiplet or part of two unique signals. Does that commentary make sense?
Yes, thank you.
Yes. So T signifies triplet, yes. To answer the question in the chat. So what's the chemical shift of this first triplet? What's the chemical shift roughly?
2.4.
Yep, 2.4, integration of 2. What's a signal around 2.4, considering that we may have an ester at play? What signal would be around 2.4? What signal is around 2.4 that's related to an ester functionality? We have someone commenting the protons adjacent to a carbonyl, such as maybe the carbonyl of an ester. Yep, these show up at roughly 2.2 to 2.7. Yep, that's a perfectly reasonable assignment. So as you see, based on the chemical shift and integration values, we're starting to generate fragments. Okay, what about this triplet of triplets? Now, triplet of triplets, that tells us we have two sets of two hydrogens adjacent, right? We have our primary splitting pattern and then our secondary splitting pattern. So we have two sets of two hydrogens adjacent to this set. So looking at our triplet of triplets, what's the chemical shift value and what's the integration? Let's continue filling in the table.
Wait,
0.2, yep.
how is it a triplet of triplets?
In this case? Oh, the problem.
Oh,
The
okay.
problem will explicitly tell us, and it's a little tricky to see at the current resolution. That's why the problem is explicitly noted that it's a triplet of triplets.
Okay, yeah, I just totally did not see the words there. Okay.
You can also when you see this multiplet pattern, it also tells us that we have multiple adjacent protons and we have a more complex splitting pattern than simply just a set of adjacent protons, right? Since this is higher order than a simple triplet or quartet, right?
Yes.
Yeah.
Okay.
So even if you can't tell necessarily that it's a triplet of triplets, you're able to get enough information to know that there are multiple protons adjacent. So this proton must be surrounded by our other two proton groups. So what shows up around 2.2? This one's a little tricky. So rather than thinking about this signal with an integration of 2 and trying to assign its identity outright, let's just think about it in terms of the surroundings. It's a triplet of triplets, right? So we must have two hydrogens, right? We must have two hydrogens surrounded by two sets of two hydrogens. Since we only have 6 hydrogens total, what other hydrogens must be around this two hydrogen group? So this two hydrogen is a triplet of triplets. what must be around, what other functionalities must surround this 2 hydrogen group? We have 6 hydrogens in total. We have a triplet of triplets, which tells us this 2 hydrogen pair is adjacent to 2 sets of 2 hydrogens. We only have 2 hydrogen groups in our molecule, and we only have 2 other sets of 2 hydrogens, right? So deductively, in order to put together our structure, what must we surround these 2 hydrogens with? How many total sets of 2 hydrogens? Does everyone get what I'm sort of leading us towards here? If it's a triplet of triplets, it needs to be surrounded by 2 more CH2s, right? And what 2 CH2s do we have? What are the only CH2 groups we have in our molecule? These first 2, right? So then all we have to do is put our CH2 groups. All we have to do is put our CH2 groups next to this middle CH2, right? This is our first 2 hydrogen signal that's a triplet. This is our second 2 hydrogen signal that's a triplet. Now, the only point of contention is, why are we drawing a ring? Well, we know that our DU is 2 and we've used up 1 DU, so we must have either a ring or double bond, right? We obviously can't have a double bond, so this is not an option. Would anyone care to comment why a double bond's not an option for the formula C4H6O2? What's an issue with having a double bond? Looking at our current skeleton, what's a problem with a double bond? We have less hydrogens. Yeah, that's one reason. But what else? We have 4 carbons already used, right? Can we draw a double bond when we've used up all of our carbons? Can we draw a double bond onto this structure when we've used up all of our carbons? No. So we're out of double bond carbons. And the second piece of evidence is, if we wanted to show an open chain structure, we would see the alcohol and aldehyde protons, right? Does everyone agree if we drew an open chain structure that we'd have an aldehyde proton and alcohol proton, right? So by virtue of the fact that these aren't there, we must have a bond and we must have a cyclic molecule. So this is our final structure that we've concluded by drawing our fragments and then putting our fragments together. So often the way to sort of deductively prove or deductively support that you have a given structure is by thinking, well, if I had this alternative, would I see the right signals? Does that make sense to everyone? Does this example make sense as we work through it together?
Professor, I'm kind of confused on like, how did you find the values for the signal?
What do you mean? Which values? The
Okay.
multiplicity
I
or
mean, you have the integration and
yeah.
then the next one. It's very similar looking symbol, but it's the signal, right?
This signal here, this symbol here, the chemical shift.
No, the next one.
Integration?
Okay, that's integration, the second one, and the first one is the
chemical shift, yes.
Shift. Okay, so like, how do you find the second one? Because I'm confused.
Yes.
Yeah.
So the raw integration values are given by your program, right? And we note that the simplest ratio between 18, 19, and 19 is roughly a 1-to-1-to-1 ratio, right? Because if we divide all the numbers by 18, we get 1. However, 1-to-1-to-1 gives us 3 hydrogens total, and that doesn't match our total, right?
Okay.
So then, in order for us to have the matching number of integrated hydrogens to the actual number of hydrogens in our structure, we're going to multiply all of our integrations by 2. And that gives us 2-to-2, which gives us 6. And that matches our total.
Oh, okay. So that's how you find how many hydrogens will be in the structure.
Yes. The other
Okay.
piece of evidence that supports a 2-hydrogen integration is the fact that we see triplet patterns, and triplets imply the existence of a 2-hydrogen pair. Does that idea?
Okay. Yeah, it makes more sense now. Thank you.
Any other questions on this example? Okay, so let's take a look at a complementary tool, and let's talk about carbon-13 NMR spectroscopy. So carbon-13 is the only carbon isotope with nuclear spin. It has a natural abundance of 1.1%, so we get a very small signal. This is good because that way we don't see splitting with the carbon nuclei substantially in our proton NMR spectra. But by averaging out multiple repeated scans, multiple repeated pulse sequences, we are able to get a very high resolution spectra for our carbon NMR using a relatively small amount of sample. Now, talking about carbon NMR, just like proton NMR, carbons attached to characteristic functional groups have unique chemical shifts. And just like proton NMR, the chemical shift is significantly affected by the electronegativity of nearby atoms. Oxygen, nitrogen, and halogens decrease electron density and shielding, moving the signal to the left or downfield of your typical alkane carbon. An sp3 carbon signal is from 0 to 90, while an sp2 carbon signal is from 110 to 220. So carbon NMR looks at the unique absorbance frequencies for different carbon-13 nuclei present in your molecule. Carbons attached to characteristic functional groups each have unique chemical shifts. The CO, a carbonyl carbon, has a very unique chemical shift of 160 to 220, with aldehydes and ketones having carbon NMR chemical shifts greater than 200, while esters and carboxylic acids have chemical shifts less than 200. The other major distinction that I'd like you to note is that an alkene chemical shift for an alkene carbon is less than that of a benzene ring. So aryl carbons or aromatic carbons are further downfield. So you should be familiar with all of these carbon NMR chemical shift values, as interpreting carbon NMR can provide you a wealth of information on the functional groups present in your molecule. And it's very useful, especially when you have carbons with no hydrogens attached. And it allows you to identify what is attached to each carbon. Does that idea make sense? Any questions? Okay, so you should be familiar, just like with the proton NMR chemical shift ranges, you should be familiar with the carbon NMR chemical shift ranges. Now, the idea of chemically unique signals is very important for carbon NMR. A signal is only observed for a chemically unique carbon nucleus. And two carbon nuclei are chemically identical if they can be interconverted via rotation or reflection, right? So benzene, even if I were to label this one carbon, even if I were to tell you, okay, that is the carbon we're going to look at, and I draw this new structure, I've rotated my benzene ring. Can you tell the difference between any of these 6 carbons? Or are these 6 carbons chemically identical?
They're identical.
They're identical, exactly right. So we'd only see one carbon-13 signal. Likewise, if you have the following molecule that is doubly symmetrical, how many signals would you expect to see?
Wait, sorry, could you repeat that question?
So this molecule has two axes of rotational symmetry. So how many unique carbons would we have? So one student says 2. How many unique carbons would we have? 3. Yep. So we'd see 3 carbon-13 signals. So you have to be really attentive for symmetry.
Is it 3 because there's 2 symmetrical like options and then the original?
Yep, there are 2 axes of symmetry. The first is
Okay.
horizontal, the other is vertical.
Okay,
Does that
thank
make
you.
sense?
Yes.
Perfect. And you can also prove this by making a model, identifying your unique carbons, rotating your model, and determining whether or not you can still identify those unique carbons after rotation. So let's look at this last structure. How many unique signals would we see for this last structure? Keeping in mind that chemically equivalent carbons are identical after rotation. How many unique signals would we see? How many chemically unique signals would we see for this following molecule? What does the class think? So the first thing to look at is these 2 carbons are unique, right? Because they're in unique chemical environments and unique relative arrangements compared to our other substituents, right? So we have 1, 2, 3, 4, 5, 6 unique carbons. So we'd see 6 carbon-13 signals. Does that make sense? Okay, so let's keep going. When we're looking at methyl propanoate, let's do an example where we assign our carbon-13 NMR signals. So we have 1, 2, 3, 4 carbons. So looking at this first peak here at around 170 part per million, what signals, what carbon NMR signals are in the 170 part per million range? Carbon number 3, exactly right. This 170 part per million signal is a typical carbonyl carbon or an ester carbon. Whoops, let me adjust this structure. There we go. So that matches carbon number 3. Okay, what about this signal at around 50 part per million? What signal would be downfield at around 50 part per million? What does that remind us of? So 50 part per million adjacent to a withdrawing group, that reminds us of an ether or an ester attached to the oxygen carbon. Yep, so that would be carbon number 4. What's this next most downfield peak going to be? What's this next most, oh, well, let me rephrase that. What's this peak that's slightly further upfield? Number 2, right? It's adjacent to a ketone. or adjacent to a carbonyl more specifically. And then carbon number 1 by default is the most upfield peak. Does this idea of assigning carbons based on their chemical shift make sense?
Yes.
Perfect. Okay, so let's keep going. And let's talk about a variant of carbon-13 NMR spectroscopy, and that's DEPT NMR spectroscopy. So quite simply, what DEPT pulse programs do is that they essentially allow the proton and carbon signal, they allow the proton, they allow you to detect carbon signals based on the number of protons attached. And they polarize and they change the amplitude and intensity of your carbon signals based on the number of protons attached. So there are 3 main types of pulses that you can do. A broadband pulse, which is your typical carbon-13 NMR. It detects all of your carbons. The DEPT 90-degree pulse specifically looks and specifically identifies CH groups, or carbons with a single hydrogen attached. The depth 135 pulse allows you to detect the CH3 and CH groups as positive signals, and the CH2 groups give a negative amplitude signals. So from these 3 different pulses, you can detect your unique carbons based on the number of hydrogens attached. So for example, your broadband signal tells you all of the carbons, and your broadband signal will show all the carbons, including the carbons with no hydrogens. The depth 90 signal tells you your CH groups. So we see that these groups are CH groups. The depth 135 allows us to identify our CH and our CH3 groups as positive symbols, as positive signals, and our CH2 groups as negative signals. The positive signals that are present in the depth 135 but not present in the depth 90 are your CH3 groups. Finally, the signals that are absent from the depth 90 and 135 but found in the broadband are your tetrasubstituted carbons with no hydrogens. Does this example make sense to everyone? And does everyone understand what each of these pulse programs tells us? The depth pulse programs allow us to detect carbons based on the number of hydrogens attached. And by systematically going through each of these pulse programs, we can differentiate what number of hydrogens are attached to what carbons, and we can use that information in tandem with our chemical shift values to directly assign the identity of each carbon atom in our molecule. So for example, I'll do this one just as a representative example. This one's a little bit trickier than usual, but it's nothing that the DEPT pulse program can't tell us. So this first signal at 130, so I'm going to label my carbons 1, 2, 3, 4, 5, 6, 7, 8. So this first signal at 130 is a tetrasubstituted carbon, so that would be carbon number 3. Right? Tetrasubstituted, very downfield. The chemical shift of around 130 is a typical alkene carbon. Likewise, the signal at 120, which is a CH group, that in turn matches carbon 4, right? That's a CH group on an alkene. That's why it's so far downfield. The next thing we'll look at is this 70 part per million signal. That is a CH group. That's carbon number 7, right? It's attached to an alcohol. It's a CH group. It's downfield. Does everyone see how I arrived at that conclusion, right? There are only 2 CH groups in this molecule, and the one that's farther downfield has already been assigned. Okay, continuing on with this. let's see, we have 1, 2, 3, 4, 5, 6, 7, 8 signals. 1, 2, 3, 4, 5, 6, 7, 8. So notice these two carbons are unique. Let's keep going. We assigned our CHs. So our CH3s, so the most downfield one will be carbon number 8. So this one will be number 8. And these other two, why is the signal disappearing? 1, 2, 3, 4, 5, 6, 7.
Isn't the third signal up there that you originally assigned as a tetra substituted carbon, isn't that the negative CH2 in the 135?
Oh, yeah, that makes a lot more sense. Okay, perfect. Sorry, I when I wrote out and I included the circle around it, somehow it completely covered it up. Okay, that makes a lot more sense. I was wondering where that second tetrasubstituted carbon was. Okay, so for our CH3 groups, we can assign them as number 8 and, well, actually, these two CH3s, since they're somewhat downfield, we'd assign them as number 1 and number 2 as their allylic. Those are somewhat downfield. And this not very downfield CH3, we can assign as number 8. Okay, perfect. We've assigned almost all of them. So let's assign these CH2 groups. The most downfield one would be number 5. The least downfield one would be number 6. So as you can see, with a DEPT spectra, you can actually fully assign all of your carbon atoms in your molecule. So this is just a representative example of how you can use the DEPT spectra along with the carbon-13 chemical shifts to assign the identity of each of your carbon atoms. Does the logic used make sense? We identify our plausible CH3s, and CH2 groups. We use our chemical shift to identify the functional groups attached to each carbon, and then we can assign the identity of each carbon using each of these 3 spectra.
Professor, like how can you tell if a carbon is more downfield? Again?
A carbon would be more downfield if it's adjacent to withdrawing substituents or if it's allylic or benzylic. The same rules that we applied for proton NMR, correct? It's the exact same logic for carbon, right?
Yeah, okay,
Does
thank
that
you.
make sense?
Yeah.
Perfect. So similarly, the carbon number 7, which is adjacent to the alcohol, it's a clear CH group, but it's also relatively downfield, which provides further evidence it's a carbon attached to the alcohol. Does that answer your question?
Yes, it does. Thank you. Oh wait, and also like how can you tell if something is downfield on the what is this, the NMR spectroscopy?
Yeah, so downfield is on the left, upfield is on the right.
Downfield is left. Okay.
The larger values are downfield. The larger chemical shift values are downfield. Does that make sense?
Yes, thank you.
Perfect. Okay, so this is a summary of the common signals that you observe for DEPT carbon-13 spectroscopy. So in combination, the depth 90 will identify all CH carbons. The depth 135 will identify all CH3 and CH2 carbons, as the depth 90 will tell you your CH carbons. So from the depth spectra, the grouping of protons on each carbon can be determined. So let's apply this. And I've given you the following spectra for a structure of an alcohol with the formula C4H10O that exhibits the following carbon-13 NMR spectra. I'll give you a hint where if you calculate the DU, 4 times 2 plus 2 minus 10 over 2, we have a DU of 0. From that information, I'd like us to go about assigning the identity of each of these carbon signals in the DEPT spectra and to start to put together a full structure of our molecule. So does anyone have some proposed assignments or identities for each of these carbon peaks? You can start off by telling me whether it's a CH, CH2, or CH3 group. That's a good starting point when reading through these DEPT spectra. So what signals are, okay, let's start with the signal. So this signal right here, what is it? So this signal at 70, what do we think it is? CH2, yep, exactly. Okay, what about this signal at 30? What does that correspond to?
CH.
Yep, exactly right. It's positive in both the DEPT 90 and 135. What about this signal at around 20?
CH3.
Yep, exactly right. We only see 3 carbon signals, but we only see three carbon signals, and we have C4H10O. What does that tell us? If we only see 3 signals for 4 carbons, what's special about that? What does that mean?
That 2 of them are chemically equivalent.
Yep, exactly right. So we have 2 equivalent carbons. Okay, so with that information, let's try to assign using the chemical shift now. So looking at the chemical shift. So looking at the chemical shift for this CH2. So we have a CH2 group. What is the chemical shift for this CH2 group? What is the chemical shift for this CH2 carbon? What is the chemical shift when we look at the spectra and we read off the chemical shift value for this peak?
69.
Sure. Okay, so then what functionality is attached to our carbon to lead to that chemical shift value, given that we know that there's an alcohol in our molecule?
Can you ask that again, please?
So what carbon would have a chemical shift value around 70? What is attached to that carbon to lead to that signal?
And oxygen.
Yep, exactly right. Such as in an alcohol, right? Since the problem tells us we have an alcohol. So this would be an alcohol carbon. Yep, perfect. Okay, so continuing on with this, we have a CH group. Okay, let's note that we have a CH group. Now, what does that CH group tell us? How many things are attached to our CH, are attached to this carbon then? If we have
3.
a CH group, we have 3 things. 1, 2, 3. That's important to note. Next, we have a CH3 group. Okay. Now, my question to you is, if we have this alcohol and we have a CH3 group and a CH group, how can we put together these fragments to get our final formula? So we have C4H10O. So by definition, one of these carbons must be chemically equivalent. And if we look at our total number of hydrogens, we have a total number of 3, 4, 5, 6, 7. We have a total number of 7 hydrogens. So by definition, we must have 2 of these CH3 groups in order for us to meet the threshold 10 hydrogens in our formula. Does that idea make sense? By definition, your equivalent carbons and your equivalent carbon is directly limited by the number of hydrogens in your structure. So then, given that we have 2 CH3 groups, a CH and a CH2 group, by definition, this CH group must have 3 things attached. What 3 things do I put on this CH group? What 3 things do I put on this CH group?
A carbon.
Yes, we'll put our 3 carbon groups, right? So we only have
Yeah.
3 available carbons, right? So what we're going to do is we're going to put our CH3, our CH3, and our CH2OH group. So we've generated a complete and full structure for our molecule using the DEPT spectra along with the carbon chemical shifts. Does that make sense?
Can you explain again where you get the 10H value from?
Oh, it's given in the formula of this molecule in the start of the problem.
Oh, okay. And
Does that make
like,
sense?
why did you have to multiply the CH3 by 2?
Because looking at our looking at our carbon and hydrogen count, if we only add one CH3 group, we know that there are 2 chemically equivalent carbons because we see less signals than the number of carbons in our formula. We currently have 7 hydrogens total. In order for us to reach the 10 hydrogens total in our formula, by definition, we must have 2 of our CH3 groups. That would be the only way to have a matching number of carbons and hydrogens to the formula, and for you to match the number of carbon signals to those observed in your carbon-13 NMR spectra. Does
Okay. Yeah, thank you.
that? Any other questions on this example? Okay, so let's do another example then. And I'd like you to draw the structure of just a general compound. So in this case, it doesn't have to be an alcohol necessarily, but a compound with the formula C5H10O that exhibits the following carbon-13 NMR spectra, and no signals were observed for the DEPT 90 spectra. So in this case, it may be an alcohol or it may be something else. One thing to note, our DU in this case is 5 times 2 plus 2 minus 10 over 2, which gives us a DU of 1. So what would that correspond to? So let's take a moment and let's try to assign the identity of each of our peaks. Let's try to share our proposed responses in the chat verbally or using the annotate tool. And we'll discuss this example in about 5 minutes. But you are welcome to share your responses in the meantime and start drawing out your potential suspect structures. You may want to start looking at the depth 135 and depth 90 spectra, as well as the broadband spectra to start identifying your carbon, CH, CH2, and CH3 groups. So let's keep working on this example. So does anyone have any peak assignments that they'd like to share based on their chemical shift values? So I'll start us off by making a little table. So we have the chemical shift value, the number of hydrogens, and a proposed structure for the identity. So looking at this chemical shift, what's this first chemical shift value?
Is it a C double bonded to an oxygen
Yep.
and also with no hydrogens attached to the carbon?
Yep, because it shows up in the broadband and not in the depth 135 or depth 90, it's a CO with 2 substituents attached. Yep, perfect. So if it's around 200, that's more of a ketone rather than an ester. Okay. So let's look at this next case. So we have something at around 45. And based on its signal in the depth 135, what kind of group is it?
CH2.
Yep, exactly right. So we have some CH2. Okay. What about at around 30? What does that tell us? We have a positive signal. And remember, the depth 90 gave no signals. So that tells us we have no CH groups. So what is this positive signal corresponding to then? What does that tell us?
A CH3.
Yep, exactly right. Okay, the next one, we have a signal at around 18 part per million. It's a negative signal. So what does that tell us?
That there is a CH2.
Yep, exactly right. And then finally, something at 10, positive signal. So what does that tell us?
That there is another CH2. No, CH3, my bad.
CH3. Okay, so with that information in hand, so we have a formula of C5H10O. We have 5 carbon signals. So how can we put together these fragments to give our final structure? Keeping in mind that it is not symmetrical, because by definition, we have 5 unique carbon signals for a formula of C5H10O. So would someone like to try to draw a proposed structure putting together these fragments? Would someone like to try drawing using the annotate tool? A proposed structure? Yep, perfect. So this structure has 5 unique carbons and matches the observed chemical shift distribution. Yep, so if we take a look at the following structure, it has the requisite ketone as well as the 5 chemically unique carbons. It also explains why we have 2 signals, one at 45 and one at 30, corresponding to the carbons directly adjacent to the ketone. Yep, so this structure looks perfectly reasonable. Any other questions on this example? Any other questions on this example? Okay, so let's do one more example. This time you're going to have to deal with proton and carbon NMR. So I'd like us to take a moment and to try and interpret the proton and carbon NMR of a compound with the formula of C9H10O2. And in this case, our du in this case is equal to 2 times 9 plus 2 minus 10 over 2, which in turn gives us a du of 5. So with that information in hand, let's start with a proton NMR. Let's look at the chemical shift, the integration, and multiplicity, and let's try to assign the identity of different peaks. So what is this broad peak at around 12? What proton matches that profile? An alcohol, an OH group, more specifically an OH group as part of a carboxylic acid. So we have an 11 part per million, or like 11.8 part per million signal, an integration of 1. It's a singlet. That is a textbook carboxylic acid proton. Okay, what other signals stand out to us? Let's go down the list. What's the next batch of signals that we see?
The benzylic protons, or
The aryl protons.
okay, yeah.
The benzylic have a different shift, but the protons directly attached to the aromatic ring, yeah, they do show up around 7.5 to 8 part per million. And this 5 hydrogen integration tells us we have 5 of those aromatic protons. So it's not quite cyclohexane, but it's more of a benzene ring, or generally an aromatic proton that have these chemical shift values around 7. What else do we see? So looking at these 2 peaks, so if we zoom into these peaks, what do they look like to us? Singlets, doublets, triplets, multiplets, what do we see? This is where it's, yep, these are triplets. Okay, perfect. So let's just note that we have a set of triplets. Okay, and we know that they integrate for 2 hydrogens each. One is 3.2, the other is 2.8. Now, what could match these triplets? So right now we know that we have 5 aromatic protons. Now, what could match these CH2 groups? What could match signals of around 3.2 and 2.8, considering that we have a carboxylic acid and an aromatic ring? What could we assign these signals to? Any suggestions? What are 2 hydrogen fragments that show up from 2.8 to 3? What are some plausible fragments? So yes, a CH2 group, and that CH2 group is next to what? What is this what is one of these CH2 groups adjacent to? For it to be around 3.2 to 2.8, what is that CH2 group adjacent to? The aromatic ring, yep, exactly right. Benzylic protons, that would be a 2 hydrogen signal. Okay, what else would lead to the second downfield signal? So we have a CH2 group, and this CH2 group would be adjacent to what to get around 3.2 to 2.8? So we have one of our CH2 groups assigned as the benzylic protons. So we checked one of them off. The other one would be next to the carboxylic acid. Exactly right. Now, since they are triplets, that means we have 2 hydrogens adjacent. So currently we have a benzylic fragment and we have a carboxylic acid fragment. How can we get a triplet? So we have two hydrogens that are a triplet. How can we set it up so we have two hydrogens next to each of these CH2 groups? How do we bring our fragments together? How do we bring our fragments together? Yep, just form a bond between these two fragments. Exactly right. And that gives us the following proposed structure. Yep, exactly right. So let's check. We have to check our work now. And let's draw and let's map our proposed structure onto the observed carbon NMR spectra. So this 179, so let's number our carbons. 1, 2, 3, 4, 5, 6, 7, 8, 9. Carbon 1 is clearly right here. It's the ester proton. This group of 4 carbons, why do we only see 4 signals? Why do we only see 7 signals? We only see 7 signals, even though we have 9 carbons. What's going on here? Why are we not seeing as many signals as we should? Does anyone have a suggestion?
Is it because 6 and 8 are equivalent and 5 and 9 are equivalent?
Exactly, there's an axis of symmetry. So as a result, only 4 of these aryl carbons are unique. And that's why 4 through 7 are observed in this region. Finally, carbons 2 and 3 are these 2 carbon signals at around 35. So as we can see, our carbon spectra directly matches our proposed structure. So this serves as a reasonable piece of supporting evidence that we have obtained our desired structural assignment and that the structural assignment is reasonable. Does this example make sense to everyone? So that's the last example I have set up for our discussion of NMR spectroscopy. So what we'll do is we'll end today's recording for today.